Thank you for coming, everyone. I'm Jacob, a senior software engineer and a team lead at Hyperconnect.
And I'm Jungmin, a junior software engineer also at Hyperconnect.
In this session, we'll introduce how we generate features with on-demand and low-latency manners for our service Azure with the Flink framework. I will divide the session into three parts: motivation, architecture, and operation. Let me give you some background on the company Hyperconnect and the service Azure. Hyperconnect is a video and AI company that was founded in 2014 and offers multiple services such as Azure and Hakuna. Azure is a video chat application and a great place to connect with people from various backgrounds. To meet others, the user will swipe left on the video live video screen. We call this discovery. In Azure, more than 180 million discoveries are happening in a day. Our team is developing and maintaining system to give our users a better experience. We call this conversion hacking. We have developed many online inference models to determine user status and try to convert them into more active participants. There are multiple ways that we can improve the performance of the system, one of which involves improving the quality of features. So we are focused on the status of pipelines to supply features. We found that there are some problems that have affected the performance of the system. The first is latency. Often we use features that were generated a few hours or minutes ago, but we eventually know the latency can deteriorate the performance or make it impossible to run any of our models. And next feature to focus on is duplication. As the number of models and applications grow in size, the features and complexity of feature pipelines are also increased as well. Higher complexities in the system create room for inefficiency, such as similar pipelines apply the same feature to different models. The final feature is stability. As the number of pipelines increases, maintaining higher reliability is the challenge, especially during the restoration. There was no update on features, so these pitfalls have prevented us from a higher gain. So we decided to make a real-time feature generation system with Flink framework. Next, I will introduce the architecture of this system. Real-time feature store consists of 3 layers. As the first layer, the user event store loads all actions of the user in real time and provides data in a queryable form. Unlike the generalized query engine, we focused on optimizing the data loading strategy to minimize the query latency according to our use case, which I will talk about more in depth later on. The second layer, feature generator, creates the features on demand. We define the format of feature descriptions to supply features and allow this layer to add, update, and delete operations to respond to changing demands in a timely manner. The final layer is feature consumer. The purpose of the prior system is to supply the features to this layer in time to get the better performance. The message sender, the various models, and the behavior store itself can be the endpoint of the feature pipeline. Next, I will introduce each part of the event store. Event store can divide by 3 parts: event processor, user query, and segment query calculator. From the source, such as Kafka, we can detect the user's behavior in the service. But often we need to attach the behavior's context to a user's profile in order to translate its event into valuable information or to understand the user's behavior on a deeper level. The implicit or delayed event are also necessary to timely responses, because a user's inactivity is often a strong implication that they are dissatisfied with our service. Event processor supports these functions, So the generated event passed to the query result calculator to get the result. And then each calculator stores event timelines, calculates the query results, and sends the sink. And there are 5 key functions in the event processor. I will describe the details and applications for each function. At first, event processor supports the enrichment function to get the user's profile only being stored in the external database. For fetching the row, the event processor asynchronous called the query and receives the results. This profile information is stored in the user profile state and then used whenever the user's next event will be. Next is context building with the events. Event processor can get information about their match during the matching events. So even though the following in match events lack the peer information, the event processor can fetch the necessary information from this state. For example, this matching context state can be used when someone requesting a friendship in a match and then find who the peer is. Similar to the context building, the event processor can detect and manage each user's segment or label. It can also be perceived as a session context. Whenever a login or purchase event occurred for a user, event processors may update the user into different user segments. These segment information pass to the next steps to calculate segment query results. The next function is generating implicit events. We cannot describe the user's behavior or intent only with the explicit events collected. Activities such as not uploading to their profile, not requesting friendships, and not spending quality time on the platform are important clues to find out why the user is dissatisfied with our service. These are crucial details to take into account when trying to convert these inactive users to the active ones. That's why event processors delicately define the implicit events and generate them whenever the trigger events come. A delayed trigger is one of the variations of implicit events, but this type of event has an important role in our push-based pipeline. Delayed events can help to calculate the query result and feature value in time. An example of this includes sending a promotion push whenever a user does not exhibit any significant behavior 5 minutes after their last login. In this case, event processor can set a timer and trigger the delayed event after 5 minutes. In this way, we can collect events and make up event timelines for each user in the user query calculator. Therefore, for efficiency, we define the custom trigger to start calculation. This trigger sends the calculation signal every second or whenever an important event is detected. Now, we are moving on to the aggregating values for windowing. We simplify the event only with the important information. The format can be defined by the event type and aggregation type. For example, if the aggregation function is count of the last 5, the abstracted value does not need any information except a Boolean value, explaining whether this event is explicit or implicit. But the aggregation function is defined as the max value recorded over 1 minute, and its abstraction should include this timestamp and amount. Furthermore, these windowed results are stored in its query result state, and also the aggregated value is calculated and passed to the next operator, segment query calculator, and Kafka sink. And these user query calculator's behavior can be dynamically managed with the query definitions. This is an example query. We can specify target events, apply functions, filter conditions, group, and window methods. Last part of the event store is segment query calculator. The method to get the segment query result is different from the user-specific query calculation method. If we adapt the same method to the segment calculation, the required resource can be increased exponentially because there is no limitations on the number of segments per user. So, segment query calculator collects the user's query result belonging to the segment and then periodically calculate with the user's latest active results. Equally important is the filtering of inactive users. So we filter the user if the last event's timestamp passed 30 minutes, as like the session division criteria. Next, Jungmin will continue to talk about the architecture of feature generator.
Thanks, Jacob. Moving along, I'd like to introduce feature generator, which consists of 4 parts. First is managing feature definitions. Since the query definitions are included in the feature definitions, the feature generator manages all the descriptions for the whole system. According to these descriptions, feature generator requests queries and constructs a calculation graph for making feature value. Next is the feature calculation, which we gain by requesting, acquiring the query results, and calculating the feature value according to the calculation graph. And results of each steps are sent to Elasticsearch for monitoring. Lastly, it sends the feature values to various sinks. Types of sinks can be categorized by the necessary number of features to be used. The first case is when one feature value is needed to get the result. For example, we can design a feature value with a module called message sender that sends messages along the GIFs to the specified user. The second case is when multiple features are necessary to get the result. We used to supply features to the online inference model to categorize the user or predict the propensity, and then send the result to the database, to the trigger, or to the event generator as a new kind of event. And lastly, I will talk about the operation of this system. There are many lessons that we learned throughout this entire process. One of them is the importance of cold starts. We understand the fast response value is greater than the precise but late response. We are using the beta distribution to predict the feature value and control the fluctuation for the early stage. And the next is the importance of monitoring. There's always a possibility that we generate the wrong feature value, and these errors lead to wrong messages or other business losses. So monitoring and making the alert for the value qualities, such as latency and abnormality, is necessary to run the system for the live production. And last is the trade-off between precision and efficiency. For example, we decide that the resource efficiency is more important than the segment feature values quality, such as precision and latency. The members and events of the segment are sufficiently large, so even though we sacrifice our efficiency, the results tend to be marginally improved.
Thanks. Thanks, Jungmin. Up to now, we've explained the necessity of a low latency pipeline and why we choose Flink to implement it. In summary, Flink-based low latency feature pipeline is a good tool to expand the candidates and improve the performance. And this tool provides an opportunity to achieve more business value. This is the end of the session. Thank you very much.